Let's find the location of the dark spots, or the minima, in a two-slit interference pattern. Here, the bottom wave has waved exactly half a wavelength more than the top wave, since the bottom one has traveled more. And as a result, the two waves are meeting out of phase here and cancel each other out, and you'll see a dark spot on the viewing screen here. Now that we know those squiggly things are waves, I'm going to replace them with lines. And now is the time when we make some triangles. In real life, this angle theta will be very, very small. So in reality, the dark spot will be down here more. And in that case, we can assume that the two lines of this triangle are equal length, and therefore this line down here, that is the extra distance that the bottom ray has traveled, which is exactly half a wavelength. We're going to say this is a right triangle, and that the distance between the slits is small d. And small d is the hypotenuse of this little triangle. Let's blow up this little triangle. There it is, just a bit bigger now, magnified. Now we can just do some trigonometry. Sine theta is the opposite side over the hypotenuse. And next we'll just rearrange it a little. And there you go, an equation to help you find your first minima. But here's the cool part. We can modify this a little bit to find any of multiple minima of different dark spots. We know that dark spots will occur anytime the lower wave has waved enough so that it meets the upper wave out of phase. So it can wave a half a wavelength more than the upper wave, it can wave 1.5 wavelength more, or 2.5 wavelength more, etc. 3.5, 4.5, you get the idea. So the general pattern here is some integer and a half number more wavelengths. And we will call that integer m. We'll call that integer m and say it starts at 0. So when you set m equal to 0, that corresponds to your first dark spot. When you set m equals to 1, that corresponds to your second minimum, etc. Okay, now let's do a little handy trick to get a slightly simpler equation. We can make another triangle where one side is L, the length between the slits in the viewing screen. Another side we'll call Y, which is the distance between the central maximum here and wherever we find a dark spot. And then the third side is just the third side. So I drew the third side and I made Y a little longer to get up to our dark spot. And I'm going to put in our angle here, which is theta. We can say this is also theta because guess what? We have similar triangles. Our triangle that we blew up before, our little guy, is similar to this one. So if we look at this big triangle, we can say that sine theta is the opposite of our hypotenuse. Oh, we don't know what this hypotenuse length is, but since theta is so small, the hypotenuse is pretty much the same as this side length. So we can just go ahead and say that sine theta is y over L. And we can put that into our equation here. So now we have maybe a little simpler equation that might help you on a homework problem or two. Okay, now let's think about where we can find light spots. Don't tune out yet. This is pretty quick going from here. For there to be a light spot or a maximum, the light from the bottom has to have waved all the way back to being a crest again. So it's the light from the bottom has traveled exactly one wavelength longer than the light on the top. Or maybe the light from the bottom has traveled exactly 2 wavelengths farther than the light on the top to match up crest to crest again. Or 3 or 4. But the main point here is that for finding maxima, instead of having an integer and a half wavelengths of difference, we're going to have exactly integers of difference in path length. So I'm going to get rid of the halves here. And we have an equation for where to find the various maxima, or the bright spots. So if m is 0, that corresponds to the central bright spot. If m is 1, that's the first maximum. If m is 2, it's the second bright spot.